Thank you for this invitation, and it's a very great conference. I learned a lot, so thank you very much. So the work I'm going to present has been done in collaboration with several labs, in particular Institut de la Vision, but also INLN in Nice. But most of this work is in the content of Dora Caruniari, PhD. So this is what I'm going to present today. So what are retinal waves? I will not, of course, explain. I mean, the biology is very interesting, but I will not have the time to explain. But what you see here on the right is the result of experiments made on retina of a mouse which was just born, and you see this pattern of electric activity spreading through the retina, and this pattern, in fact, are ubiquitous. They appear in many species, and it's important to understand that this pattern appear a bit before birth and they disappear a bit after birth. And they are known as being completely fundamental for the shaping of the visual system. They contribute to the shaping of the retina, to the shaping of retinotopy, or for binocular rivalry. So they're absolutely essential, and they appear in many vertebrates. Yet there is a wide variability in this retina. So even if they appear in different types of species, they have different characteristics like distribution, speed, etc. This is what you see here. Can you see? I hope you can see my mouse on the right, left. But there is also a variability during development. Even if the window where these waves appear is short, you can see a few days. You can see evolution, for example, here on the acetylcholine synaptic strength, so which is measured by experimentally. So I'm going to come back to that. One of the main points in my talk. So you have change of physiological change which induce change in the waves during development. Pharmacology also play a role. If you just input drugs or some agonist or antagonist, you can dramatically change the waves. And finally, and I'm also going to talk about that today, you observe a spatial variability. Even in time window where you observe wave, they can be of different size, different duration. So today I'm going essentially to explain what is on the right panel. The left panel is the object of another paper which has been published in a scientific report, but today I will focus more on what is on the right. So the question which is here is, well, we have a large source of variability, but a large type of variability, but what are the source? And what I'm going to show you today is that we can explain all that with a unique global mechanism, which is actually the closeness to bifurcation. But let me come to that. So now, if you want to, if you want to go to experiments, in fact, the first thing is to understand what makes these waves. And neurophysiologist has made a very clever experiment, which essentially isolated three main components for these waves. The first one is a bursting of specific cells in the retina, which are called starburst amacrine cell. In abbreviated Cessac, starburst amacrine cell, and these cells are bursting. So this is the first thing. The first ingredient is that in between the burst, there is a refractory mechanism, which is quite long. It can last, several seconds, even minutes. So this refractory mechanism is related to a slow after hyperpolarization, and it is very slow. The third point is that this starburst amacrine cells are coupled together via acetylcholine. And this can be seen again experimentally. Here you see that when in normal condition here and here the cells synchronize, but when you add some drug, some cocktail which make somewhat neutralize acetylcholine, you remove synchrony. So it's known that acetylcholine play a central role here. Now, on the modeling side, there are actually have been many models and very good ones. Some of them really compare well to simulation, especially Henri et al. Model was done in collaboration with Blin Sarnagor, who is one of the world's specialists of this retinal wave. So there is a very, very good job on numericals, on the modeling side, sorry. But actually, to our best knowledge, none of these models were integrating the three components that we observe in physiology. So this is what we wanted to do. So now I'm going to quickly present the models that we have chosen. So the idea is to produce these three mechanisms. So the bursting will be made with the classic, well, almost classical Maurice Lecard models that you can see here. The only difference with classical Maurice Lecard is that the potassium variable here is fast. Normally in the Maurice Lecard it's rather slow. Here it's fast. It's a few milliseconds. So I want to insist on one point. You don't see sodium in this equation. This is because experimentally people have shown that sodium is not playing any role. If you block sodium with the cocktail biologists know how to make, you still observe this bursting. So they know that it comes from calcium and potassium has to be fast. The second part of the in the model is here how to model the slow after hyperpolarization current, which we see here. And it is modeled by a current of this type, where I'm going to explain the variable R. It's a potassium current, but in contrast to this one is very slow. Now, and the last term is acetylcholine coupling that I'm also going to explain. So concerning the slow after hyperpolarization current, it's due to calcium dynamics. So when the voltage of the cell increases, you have calcium entering into the cell. And I think Christophe spoke about that yesterday. When you have 4 molecules of calcium, which are sticking on what is called calmodulin, you realize you make a saturated calmodulin, and this calmodulin saturated will fix on terminal, and when 4 terminals are open, you open a channel. When 4 terminals are bonded, you open a channel. So this explains why here you have a power 4 in the conductors. So you have, this is the probability that 4 gates are 4 terminals are gated simultaneously, and this power 4 is actually very important. So, well, I don't want to enter into detail, but basically, all these dynamics can be expressed this way. So here you have the calcium production. Here you have the calmodulin. So you have the saturated calmodulin fraction, and we have this power 4C that Christophe was talking about yesterday. And finally, the equation for R is a classical kinetic equation. Okay. And now concerning the acetylcholine interaction, well, you see that actually starburst and macroin cells are making a quite regular grid, which is nice because we can model that as a lattice. And now we know, again from experiments, that in this stage of development, the acetylcholine is bound to nicotinic receptors. And essentially, this means that you need 2 molecules of acetylcholine to bind on the channel to open it. So you get this function where you have a power of A2, where A is a concentration of acetylcholine. So in the end, you obtain this equation where you have the dynamics here for the burst, here's the dynamic for the hyperpolarization, and here's the acetylcholine coupling, which here, where the conductance depends on the cells AG, which are connected to the cell I. So you have a system of equations that we can summarize here. So we have actually 7 equations per cell. So this means that we 6 equations per cell. Sorry. So it's a big system, and in fact we have a lot of parameters. But what we are going to use to make the dynamical system analysis is the fact that we have in fact different time scales. It's a slow, fast analysis that Mathieu would appreciate, but we have 3 time scales here, essentially. We have the fast time scale of bursting, which is of order millisecond, the medium time scale of calcium and acetylcholine, which is of order second, and the flow variable related to slow after okay, you understood, which is of about 1 minute. Okay, so now to make the dynamical system analysis, I'm going to do something that, well, many of you know. I'm going to consider that I have first the fast dynamic, and I'm going to consider that the SHP conductance and the acetylcholine conductance are slow. So even more, for the moment, I'm going to consider them as constant, and later they will vary slowly in time. So this means that in my equation, I have here a parameter which is the SHP conductance, and here's the acetylcholine conductance. And from that, you can make a two-dimensional bifurcation diagram where on abscissa you have GS, SHP conductance, and GA, acetylcholine conductance. And if you look at this bifurcation diagram, we have 4 regions, A, B, C, D, where D is very tiny, actually, and so tiny that in the beginning we didn't, we thought it was not important. In fact, it is absolutely fundamental. I'm going to come to that. So here I'm doing the face portrait that you observe in each region. So you see the null lines and the classical labeling for fixed point and unstable focus. And the red lines correspond to unstable manifold of this saddle, and the blue line corresponds to the stable manifold. So in region A, you have this face portrait. In region B, you have just this face portrait, and here you go from one to the other by crossing the saddle knot line here. In region C, you have a unique limit cycle, which is stable, and you go to it by, it depends where you are in the fast plane. So you have different type of bifurcation. In particular, you have a homoclinic bifurcation here, HC, which is there. And finally, in region D, which is again the most interesting, you have coexistence of a sink, a stable fixed point, and a limit cycle. So we have seen several times such similar cases. Yesterday Eva was talking about a stable system, but in her case it was two stable fixed points. Here we have a fixed point and a stable limit cycle. So now, if we when we consider in fact, what is very important, I am going to explain that a lot of time. In the system will dynamically come back recurrently in the region D, and that's why this region is very important. But now, when you are in region D, you will stick at the saddle, the sink, the stable fixed point. So this means that you have no way to trigger burst, except if you add noise. So this is what we have done. If you add if you have noise in the system, what will happen is that after a certain time, you eventually will be lead to the stable limit cycle. So you have this oscillation. Now you can go back and this is what you see here. Now, what interests us here, and this is this spirit very different from what people are using usually in stochastic analysis. What is important to us is not the fast variable, the calcium variable, because it's the one which will trigger SHP. I'm going to explain that in 1 minute. So in fact, if you look at calcium, you see that during bursting, it will increase and then decrease. What interests us is that we have that calcium be large enough to trigger the SHP mechanism, which means that if you want to compute the probability to get something significant, you not only need to compute the probability to get there, which will be a first passage problem. You need to compute the probability to get there and to stay sufficiently long so that calcium reach a certain threshold, say. So I have no idea how to compute that. Maybe if probabilist people know how to do that, it would be very interesting, because I think it's more complicated than just computing a first passage time. Anyway, now we can come to explain what is the bursting mechanism, and yes, the bursting and hyperpolarization mechanism. So this is explained here in word. The cell is bursting, so when it's bursting just long enough, you rise the calcium. So calcium is increasing. If you rise the calcium, you have this mechanism of triggering this SHP. So this means that at some point the cell feels a negative current, an inhibitory current. And as we are going to see in 1 minute, it makes a bifurcation so that the cells return to rest. So when it is at rest, calcium is reducing, SHP is reducing. So at some point, the cell get back to the point where it can be excited again and reproduce again bursting and so on. So this can be explained in this three-dimensional diagram. You start from a fixed point. If you go to the lead cycle, if you stay long enough, you will produce calcium bursting. Then you will start to activate SHP. So this means here that you will raise the variable S and then the variable R, which triggers SHP. So at some point you will stop the bursting and return back to rest. So this can also be explained in this diagram. Basically, this means that this motion here in the space CRS in the fast plane corresponds to the fact that when you are at rest, you jump to this state. So you will have an increase in the GS variable, the SHP conductance. This means that eventually you will cross this bifurcation line. So this means that you will lose oscillation, but you have calcium which is very high, and calcium will need a certain time to decrease so that you return back and you can reactivate bursting. So now I would like, yes, and as I said, it's difficult to compute the probability to trigger a burst, in particular to stay long enough for calcium, but we can compute it numerically. This is what I have done here. So this is region B, and here this is the probability that calcium reach a certain threshold. And you see that this is very interesting because the probability is 0 here in the region A and B. It's 1 in region C because you stay on the limit cycle. And here in the region D, the transition is very sharp. You can see here 3D, which means that when you are in this region D, in fact, depending on where you are quite sensitive to noise because you change the probability to start a burst change dramatically, very steeply when you are in this tiny region. And this will be an important point later. Now we would like to study the effect of the other cells because here I was considering an isolated set, but in fact, in general, this cell is connected to other by acetylcholine, and here we have the acetylcholine conductance, which depends on the acetylcholine production of the other cells, and on the parameter GA that I'm going to explain later. Well, I didn't explain too much how AG is produced, but it was in the equation I have shown, and I was a bit fast. If you have questions, I can explain it. Anyway, what I want now to tell you is that when a cell is at rest in region D that I have lost, but as soon as it is at rest in region D, then do we have it? No, I don't have it. Sorry, I know. Okay. When I am in this region D and when my neighbors are bursting, they will increase the level of acetylcholine, which means that GA is going to rise. So at some point, the cell might, depending on the value of this parameter, might cross this bifurcation line and trigger and enter in a region when it starts to burst. So here, before the bursting was induced by noise, it's induced by the fact that neighboring cells are bursting themselves. And this is the beginning of the story of a wave. Now it's very interesting because when the cell I enters in this region and starts to oscillate, it will produce acetylcholine, which means that it will increase the level of excitation of its neighbors. So this means that cells are coupled in a very clever and nice and nonlinear way. Let me explain this. So here again, we have the conductance, and G, the small GA is a parameter which will control so much the maximum value of the conductance. So here I'm considering two cells which are coupled together, and I make the first cell bursting by some kick, and I look at the effect on the second cell. So if the first cell in black we have a zero conductance, of course, we have no impact on the second cell. Now, if you start to increase GA, the bursting, is this blue line, when the bursting of this cell will trigger the burst of the second cell. But now you see that because this cell is bursting, it will increase the level of excitation of the first one. So you see that the burst duration is prolongated. So this is a very nice coupling mechanism because these two cells interact, and there is kind of cooperativity mechanism that I'm going to discuss in more detail in 1 minute. Okay, now the point is that you see now dynamics will depend on this parameter GAA. I'm coming back in 1 minute to that. Now, you can really summarize the dynamics of a wave in this bifurcation diagram thanks to this figure. So it's exactly the same thing, but here I have a color map which shows, say, the level of the average voltage of the cell or the average level of activity of the cells. So you have regions where the cells are quite active, and here, of course, you have black. And basically, the mechanism of a wave for a cell is either, well, assume that the cell is excited by some neighboring wave. It will enter in this region. It will start to burst. Then it will start to produce calcium and SHP. So it will get out of the region of bursting and return back to rest. This is just a sketchy diagram, just to make you understand the general mechanism. And the point is that what you can show is that this region D, which was so tiny, is in fact recurrent. And part of the reason why it's recurrent, well, it comes on one hand for the parameters, but also from the fact that we have a power 4 in R, which means that we are always returning in a region where GS and GA are low. I can explain that in more detail later. Is our question. Now, I want to study this effect studied by Zeng et al., showing that the acetylcholine efficiency is decreasing during the evolution of the wave in a few days. So what will be the impact on the dynamics of waves? So in fact, I'm going to show you that we can observe 3 regimes, and that I'm going to explain. It's just one example of this regime. I'm not going to comment more than that. I will explain in more detail what are these 2 regimes in 1 minute. So basically, when GA is very low, so here is a one-dimensional plot of the wave. So sorry, here is this space, here is this time, and what you see is the calcium concentration in color. So when a cell starts to burst, you see an increase in activity, which corresponds to a high level of concentration. And then there will be the hyperpolarization, which actually corresponds to low calcium. And then you return to the ground equilibrium concentration, which here was fixed to 88 nanomoles, yes, in the model. So you see the effect of one cell bursting. It bursts, and then it leaves a trace of hyperpolarization. So when GA is very low, you just observe point because cells are not coupled together, because acetylcholine conductance is not strong enough. Now, if you start to increase a bit GA, you start to see a bit of, well, wave extension. If you go on increasing it, you start to see something looking like a wave of propagation. The interesting regime arises there, where you see that waves are propagating, but at some point they can, for example, here this is clear. The wave propagates, but at some point it hits the SHP trace left by the previous wave, so it stops. So here the waves are competing together. If you increase again, in fact, you see that waves are somewhat more and more cooperative. And at some point, well, there is a kind of percolation point where waves are now spanning the whole space. And this is something that we would like to explain. So I'm going now to explain rapidly what are the three regimes, considering the wave propagation on this form. We consider the radius of the wave as a function of time, and it's a c, which is we can call the velocity, even if it's strictly this one. C t to the z, where z is the diffusion coefficient. So if z is equal to 1, it's a ballistic transport. If z is equal to 1/2, it's a normal diffusion, but it can be in between. And what you observe is that this exponent z in region 1 is smaller than 1. In region 2, it's very close to 1, and then it decreases again. And here, this is the speed. And this line, I'm going to explain it later. It's a theoretical estimation. So now I want to explain the different regime. Basically, if the GA, the maximum acetylcholine concentration is too weak, you have no propagation possible. The individual cells cannot burst. Cannot make the other cell burst, which is what you observe here. Now, when you are in region 1, it's very interesting because when a cell bursts, it increases in some cells the probability that the neighboring cells it can burst. The acetylcholine is not strong enough to make the transition, but it just increases the probability to have a transition. Which, and remember, all this the probability to induce bursting is steep in region D. And actually, this is what represented here. If you modify a bit the parameter, you modify this distance, so you increase the probability to trigger a burst by noise. So this is this regime, and here this is a color map of the conditional probability of the cells of cell occupancy in this plane, condition upon the fact that you are bursting. So you see that the cell spends most of this time in region D, but sometimes it can go there where it is closer to region C, and you also you increase the probability to trigger a burst by noise. And this explains why we have this anomalous transport, because here, it's where it is. Yeah. Z is lower than 1 because it's not a classical propagation, it's a propagation by saltation. I don't know how you say that in English, but by jumps. Okay. Now in region 2, we have now acetylcholine strong enough to induce a wave propagation. So this is what now the cells are spending sometimes in region C and sometimes in region D. So when they are in region D, they can burst due to noise. Then they increase the acetylcholine intensity, and some cells go to region C. So they start to go to the limit cycle. So this corresponds to this regime, where in fact here the cells are the waves are competing together. This is what I was saying. A wave can provide that, but at some point it will be stuck because there was another other wave before, and here you have a black region corresponding to hyperpolarization. So here you get a very random regime. Waves are ballistically propagating, but the patterns are very complex. And the last point is that when the acetylcholine is large enough, you get this synchronic pattern. So here the cells are spending most of the time in region C, and you get this synchrony. I just want to explain briefly why the exponent is going below 0. In fact, here you have a problem. If you want to characterize how a wave propagates, when two waves collide, how do you characterize propagation? At the very point where they collide, you cannot define the propagation anymore. What we wanted to show here, so what we have done is that we consider that the radius of the wave stops when it hits another wave, but we still consider that the time goes on. So this leads in the end an exponent which is lower than 1, but it's just an artifact of our choice. The point here is to show that in fact this is a region where waves start to cooperate. So in region 2, the waves were competing because of the SHP landscape. In region 3, they are starting to collaborate and, in fact, making these periodic patterns. Voilà. So this is very interesting because, in fact, this gives a picture of what could happen during development. And in particular, this shows that there is not one regime of wave propagation, but different ones. And in particular, this transition between a competition regime, which is quite disordered, and a cooperation regime. Now, to finish my talk, if I can, I would like to go to what you like, some of you. I would like to describe this wave propagation by a PDE. And this is what we have done. Basically, we consider that acetylcholine conductance, the SHP conductance are now fields, and we are going to write equation for this field. And what makes this analysis difficult is, as you see, the wave propagation depends on the history of the landscape. So you have a propagation in a random landscape which depends on the history of the previous waves, at least in region 2. So while we do something classical, we consider that GS and GA are spatiotemporal field. We consider nearest neighbors interaction because we want to have a Laplacian. We make continuous time limit, and we make a mean field approximation for acetylcholine production. Basically, we compute the average production of acetylcholine depending on GS-GA. So GS and GA. So this gives you this profile. So here, the average acetylcholine production is 0. Here is 1. And you see that there is a sharp transition which corresponds precisely to region D. And now, while I make a long story short, you arrive at an equation of this type. So omega is this function. So it's a nonlinear function of GHGA. So the equation of acetylcholine conductance obeys a transport equation of this type, where you see that, in fact, you have a diffusion coefficient here. you have Laplacian, but applied on this nonlinear function, which makes the story a bit difficult. And you have a source term which contains a dissipation of acetylcholine and a production of acetylcholine. So this term in general is slightly negative, but it's a forcing term of the equation. Now, I don't want to go further because we don't know so much about this equation. What we know is that we can rewrite it this way. It's straightforward mathematical derivation. And now you see that what we have now is the Hessian of H and the gradient of H. So you can show here is a numerical plot of the gradient of H in this space GHGA. And again, you see that it's essentially important in region D. Or in other region, it is essentially zero. So important things happen here. And here, this is a view of the Hessian. So this is the Hessian here is a 2x2 matrix. So what we have plotted here is the first eigenvalue in color code. And you see that it is important again only in region D. And the arrow corresponds to the orientation of the eigenvector associated to the first eigenvalue. And here we have the same for the second eigenvalue. While the picture is not very good, I'm sorry, but essentially you see something which really looks like the bifurcation map. And you see that the important things are happening in this region as we expected. So the point is my second question to mathematician. We have absolutely no idea how to use this equation or to study them. And actually, I was really scary when I discovered that, I forgot to say something. I'm going to tell it later. These equations are very efficient, actually, because with them, using some physicist approximation in tricks, we are able to find the region where, as a function of the parameter, this blue line, where you know that before you cannot have any wave, we can compute the wave speed in the ballistic range, which is this line that I was mentioning before. And you can also compute the value to enter in region 3. Actually, I think we can also compute the synchronization transition, but it's I didn't do it. Now, I was saying that this equation scared me because I realized that you can make a simplification. For example, you consider that the landscape, yes, because what I forget to say is that, I said it, but when you have wave propagation, the landscape of SHP of GS is not flat. It's a random landscape. So you have to consider the propagation of a wave in a random landscape, which has been imprinted by the previous story. So it's very difficult. But if you consider that this landscape is constant, you can show that this equation is some kind of has a strong link with the Kardar-Parisi-Zhang equation, which makes us very scared because, we know that Kardar-Parisi-Zhang equation is very difficult. I think that there was a field medal recently studying it with the renormalization group, and I think it's a very difficult problem. But maybe there are some ways of getting something out of this equation. If there are physicists in the room, I also would like to mention that in some approximation, it is also close to what is called the Zhang model of self-organized criticalities. Actually, this is the same Zhang, which proposes also a model of self-organized criticality, which can be written by a singular diffusion equation. Voilà, I'm finished. Thank you very much. I hope I have not been too long.
Thank you, Bruno. Questions in the room?
Thank you, Bruno. I have a question about your first question for people who like math. I think I miss the kind of noise you add to your system in order to start the cycle. And I was wondering if you try to use a finite effect, such as in the paper by Henri, Thielen, and Pagdaman, and so.
So do you see my slide?
Yes,
you are speaking of that. So the noise is a classical Brownian noise, so there is nothing special here. I read a bit the literature. I remember I read especially a synthesis paper by Jonathan and Olivier, Jonathan Touboul and Olivier Forjas, and they were dealing with this first passage problem, but I didn't find anything to the point again is not to compute the time where you go to the limit cycle, is to find the probability to go to the limit cycle sufficient and to stay sufficiently long so that the calcium reach a threshold. And so this means that you not only have to consider the first equation of V, you have to combine it with the equation of C, and you see the oscillation of C due to dynamics. I was thinking of maybe Fredlin Wenzel saying that this set is in fact is an equipotential set, but I don't know how to do that.
So you add an additive noise,
yes,
Brownian noise on which component? On any
on
component?
the dynamic of V. Yes, it's a good. Yeah, I should have said it. Can you see it here?
Yes.
The dynamic of V, just of V. Yes.
Okay, so in the work of Michel and in the PhD thesis of Gilles,
Henri. Okay.
yes, the noise was added in the linear part, and it to take into account the finite number of channels.
Okay.
And okay, we can discuss later.
Well, with great pleasure.
The first step was to use a continuous time Markov chain, and then they were able to write the same kind of equation with a Brownian motion, but of course the intensity has to be very small.
Okay.
And it was something like the square root of S minus 1 minus S.
Okay, but I would be very pleased to discuss that with you. Several times you helped me with this project.
En fait, j'ai changé tous les labels, c'était un bordel. C'est un
Olivier, Romain, on t'entend.
C'est nettement égal.
Non.
Parce que
Romain, on est 500 à t'entendre, c'est
bon.
Okay, so yes, Tian, I would be very pleased to discuss with you. Thank you. Other questions?
Other questions in the room? Okay, I think we're all tired, but
Yes,
thank
sure.
you for your very interesting talk, Bruno.
Thank you, Patricia. Thanks to all.
Just checking on YouTube, but yeah, Claudia Vargas said very nice talk too.
Thank you, Claudia.
And I think that's it. Yes. So thanks a lot to all the speakers.